Okay. So so now we can actually take a look at these various orders. And so the first one that we want to consider is the so-called monopole. And so if I write down the monopole contribution, right? So let's take the monopole. Now the monopole, I'm just going to write down the field of the monopole here, which is just Ke over R integral rho R prime integrated over V. Okay, and of course, let me just quickly, if I look at this form over here, then indeed the first order is just 1 over R, right? Because this is n equals to 0. And P of 0 is simply 1 here. Given 1, and so indeed the first order is just 1 over R. Now, since I'm integrating over R prime, right, in the space of V prime, I can just take the 1 over R out. So I get Ke over R integral rho as a function of the prime coordinates integrated in the V coordinates. Now this is something that we should all be able to do, because this simply is equals to Ke Q R, in this case where Q is simply the integral over rho dV. Right? So there's nothing here, right? We integrate the entire charge density over just the entire volume. And so I'm just getting the total charge out. Okay, so this is the total charge. And so here we arrive at the same notion that if I have some charge distribution, but I'm going very far away, then something like this, where this is R prime and this is R. So in this case, if R is much bigger than R prime, then this just looks simply just looks like a point charge. And this is exactly what we started off with. The assumption is that if we go very far away, I'm simply going to get a point charge. Okay, so now let's take a look at the next order. Okay, so the next order would be when I have n equals to 1. So if n equals to 1, I'm getting R prime over R, and I get P1, which is just x. Now x, as you can see here, is the cosine of theta. Let's make this a little bit more explicit. So indeed here we can see that to write it in this form, h is simply R prime over R, and then x is cosine theta. So indeed here, instead of x, we got cosine theta. And so if I look at the dipole, if I look at the dipole contribution, if I look at the dipole now, then what is it that I have? So I get phi of the dipole is now given by Ke over R, the integral of rho as a function of R prime. Then I get R hat dot R prime divided by R in V prime, which here is simply equal to Ke over R squared. Right? I can take this R out of the integral because I'm integrating only over the prime coordinate system. And I can even take r hat out, and I'm just integrating over rho r prime like this. Now, I just want to highlight that this here is actually a, is a vector quantity, right? I'm integrating, this is a scalar, right? The charge density is a scalar, this is a vector, and here we've got a scalar element. And so the whole of this is a vector. And so I can actually name this P arrow in such a way that I can now write Ke over r squared P dot r hat. And so if I now look at this, since this is a vector, I can actually, I've defined a so-called dipole moment. So this is the dipole moment given by P. And this dipole moment just adheres to vector manipulation rules. Okay. So for example, I could add two dipole moments together, but I will have to do it in a vector addition way. Okay, so now let's actually take a closer look at this, at these first two things, right? So we've got the monopole and the dipole. And so I wanna give you a good question in the following sense, right? I know how to define my monopole here, and I know how to calculate my dipole given this. But are the monopole and dipoles, are they the same for every observer? Will everyone agree on the same P? Okay. So the question is, oh my goodness. Will every observer agree on the same moments? Okay, I'm going to give you a minute or two to think about this, and then we'll come back to discuss this question. Okay, anyone want to give it a go? Will every observer agree on the same moments? Okay, nobody wants to give it a try? Okay, let me ask the question then like this. So what if I change the origin? Or, well, what if I add a displacement? Now for Q, this doesn't actually matter, right? Because the monopole moment, we can say, is just Q. It's given here by this expression over here. And so Q here simply remains, okay, this doesn't work again. Oh, okay. I apologize for the technical snafu again. And this doesn't work. Okay. Let me come back and fix this. Okay, let's see. Q is simply the integral of rho r prime dv prime. And so indeed, it doesn't matter where the origin r is, right? I'm simply still integrating over the entire volume where rho exists. So this does not change. Does not change. Let's see, if r prime goes to r prime plus some constant vector a. But what happens with p? Now p here is given by r, the integral of r, and let's call this 1 prime rho r prime dv prime. But this here now is shifted with respect to some a. And I get rho r prime dv prime. Here I can split this integral now up into two pieces, one with the r prime times rho. So indeed I get r prime rho r prime dv prime minus a, which is a constant vector, rho r prime dv prime. This is the original p, so this is p1 minus a and q. And so indeed, in this case, just as an example, the point of origin matters. In fact, even if you have just a point charge, where normally you'd expect that the where the dipole moment, you know, well, okay, yeah, where you don't expect there to be a dipole moment, if it's at the origin, right? So the dipole moment does change depending on where you shift the origin. right? If I offset it by a constant, then I'm actually seeing that, my dipole moment changes. So depending on where you are, my dipole moment is actually different. Okay, are there any questions so far? Okay, I don't see anything coming up. In that case, let's take a 5-minute break and we'll come back at 5:05 and we'll continue the discussion. We're going to take a look at we're going to take a look at the different moments in the magnetic multipole, and then we're going to take a look at a few examples. Okay, let's get back at 5:05. Okay, welcome back, everybody. Let's take a quick look at some of the questions that were asked. So Poon Shun Chi is asking, is there a typo in the expansion of r minus r prime? The sign of r hat dot r over r. Let's see. Which page are you talking about? On this one, there is not even a sign. Let's just add that here. This one. Let's see. Oh shoot, okay. This should be a minus sign. This. Right, it's r minus r. And so, right. Yeah, this should be. Oops, sorry. You mean this one? Final line? No, that is correct. Yes. Did I get that right? Yeah, that should be a plus. That should be a plus. Yes. Do believe you're right. Okay. And then Simon is asking, if I observe a dipole at a very far distance, wouldn't it just look like a point charge? Well, if you talk about a dipole, in which case a physical dipole, then as Yatwang Sun Yatwang is saying indeed. So I've got a plus charge and I've got a minus charge. But if I look very far away, let's say I'm here, then they would look something like this, a plus and a minus, or you put them very close together. And so what you'll see is just this thing here, which then this is simply looks like a zero charge thing. Does that answer your question, Sam? Excellent. Okay. Again, I can't stress enough that you are encouraged to ask questions always. Don't be shy. Right? There are no good or bad questions, just missed opportunities for asking questions. Okay. So let's take a look now. We've considered this in terms of the the monopole and the dipole for the electromagnetic potential. Sorry, the electrostatic potential. What if I now consider the same thing, but for the magnetic monopoles? Okay, so now we're going to take a look at the magnetic multipoles. And so here, recall that A as a function of R is just Km, the integral of J over R minus R prime dV prime. Okay, and so we can do the same thing for the for the vector potential. Now, just looking at this form, we can start noticing a few things. Okay, actually, let me write this in a slightly easier to parse form. So instead of considering in a volume integral, let me consider it in some line integral with a constant current going through it. So here we can also write it like this. Right? So this is just a loop of current I. So let's take a look at, in this case, the expansion here. So what would be the first order if I do an expansion like this? What would be the first order? Okay, now we can take it step by step. What is the first order in R minus R prime? Anyone? I mean, we can take a look at this slide. No, this slide over here. What's the first order in R minus R prime? Oh, sorry, 1 over R minus R prime. 1 over R, very good. Okay, so if I just look at the, let's say, so-called monopole contribution, then I'm just getting a 1 over R, but because I am integrating over the prime coordinate system, I can actually take it out. So I can just do KMI over R. And then my integral is just dl over some loop. Now, what is the integral of dl over a loop? Yeah, okay. Punchen is saying the length of the loop. What is the, well, okay. What is the length of the loop in this case? And again, bear in mind, right, we're not integrating dl over a loop. We're doing a vector integral over this loop. Right, so it's not just the length of the loop. It's actually, if I go around the loop, it's all these little vector contributions, all these changes of the vectors. So this, indeed, the loop, I just end up in the same place. Now, this is something that, shouldn't be very surprising. Remember that, if we compare to some phi of the monopole, which is simply related to Q, the charge. But, as most of you know, there is no magnetic equivalent of charge. So you could even state that this is simply an equivalent statement to there are no magnetic monopoles. I.e., that the divergence of B equals to 0. Okay, so there is no magnetic charge, and so even just by comparing to the scalar potential results, we could have deduced that the monopole contribution to the vector potential is ought to be 0. Okay, what about the dipole moment? So So this would be the lowest contribution for the vector potential. And so let's take a quick look again at what we expect. Put this here, nice in the middle. And, well, okay, let's take a quick look. I have that, now I'm looking at the second term. So this would be r hat dot r prime over r squared. So I can do the same thing here. I could write 1 over r squared integral of r hat dot r prime, and here is j dv prime. Okay, and also j prime, if you will. Well, okay, we didn't write r prime, so probably there's no need to write j prime. Just again, remember that j is only exists in r prime. Now, similarly, if I'm only considering a, if I consider this to be a line integral, okay, for a line, I could also write km. Oops. Yeah, there's some kn over here. I could write km I over r squared, and indeed a loop over r prime cosine prime, and then dl prime, like this. Okay, so this is just over a loop of current I. Now, I could actually end up rewriting this, and it's a lot of algebra, so I don't want to explicitly or necessarily go through an expression like this, but it actually turns out that I can actually write the following. I could write this expression. Okay, I could write this expression. Actually, the expression is the easiest in this loop. Okay? And this is actually simply given by km over r squared m cross r, like this. Sorry, okay, let me do this better. Oops. Doesn't want to go. Okay, I can rewrite this as something very similar to what we had before here in the dipole moment, where we now define this as p dot r hat. And so here I can write m cross r hat, and well, we can take a look at what this is. For the loop one, it's easy. M is simply the integral, or it's I, the integral of a, like this. And let me also show you the expression for, in terms of the full one. I need to quickly look that up. Let's see. Okay, because it is a bit of a, I need to make sure I get all the crosses and stuff right. So this one is, right, okay. So this one here can actually be rewritten as, so this m here is simply given by the half of the integral of r cross, oops, this cross j dv prime. Okay, it's a little bit more difficult to write. Okay, so again, in order to prove this, we're actually going to need a little bit of well, tensor algebra manipulation, but generally you can show that this is R prime cross J. Okay, so this is just R prime cross J. You can write this that way. But also where the R here is taken to be outside, and then R hat, cross that. So M is just given by this. Or in a loop, it's a slightly easier form. It's just I and then the integral of the area itself. So it's just the size of this little element in which the loop is going over. And we're actually going to, I'll show you an example how you can calculate this. So typically, you will actually use this formula more. This is really more for completeness. I mean, this tends to be a much more cumbersome calculation. So let's now take a look at, let us take a look at examples. Okay, so we've done a lot of work to prove this multiple expansion, to consider the different various orders, but how can we actually use this to do our calculation? And so let's take a look at two examples where we're actually gonna make this explicit. Okay, so let's take a look at an example. Oops. Let's take a look at an example. So the first example is a sphere of radius r, just at the origin, carries the following charge density: rho r theta, right? Rho is a function of r and theta. Okay, I'm going to omit the primes, but okay. So I've got k, which is some constant, r over r squared, r minus 2r sine theta. Again, as a caveat, these are all in so-called just in the prime coordinate system. So we now have a sphere which has a particular charge distribution. Has a particular charge distribution given by this form. And so the question is, well, how can I find? So the task here is, just find the potential, and we can say on the z-axis, but the crux here is far from the sphere. And so now we are, we have at our disposition, we have the integrals that we can do to get the various different poles. So here I can look at the monopole and I can actually calculate what would be the monopole contribution of this charged sphere. Okay, so it's no longer a uniform charged sphere; it's actually a really charged sphere. Well, let's take a look. Let's look at the monopole contribution. And here, what do I have? Okay, so in R, I can do the integral from 0 to big R, right? There's a sphere of a particular radius, and well, I collect all the various. Move this over a little. Actually explicitly phi monopole equals, okay, so I take the k outside and now I collect all the different contributions of in terms of r. So I know that this is simply r over r squared, and this is big R minus 2R, and then, if I want to integrate this on the spherical coordinate system, I get R squared dr. Okay. Again, bear in mind that these are all in the prime coordinate system inside. It would be a little bit too much to write primes everywhere, but this is actually the relevant integral to do in the R coordinate system, because I also have to go from 0 to pi in theta, and then from 0 to 2 pi in phi. Now the r's cancel out. Okay, so this r squared here cancels out with this r. Oops. Okay. So this r squared here cancels out with this r squared here. And so what we're left with is a relatively simple expression here, where we have r squared r minus r squared r, and from 0 to r. Okay, and then some other stuff in terms of pi and phi, but as we'll see, this dot 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 and dot 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 from 0 to pi, 0 to 2 pi. But if I now actually put this expression in the first part here for the monopole contribution, this part here goes to 0. And so indeed, we can see that the monopole contribution to this charged sphere equals to 0. In other words, the total charge integrated over this entire sphere is given by 0. So if I go very far away, I don't actually have a contribution from the charge itself. Now let's take a look at the dipole. So now let's take a look at the dipole. So phi dipole. Okay, so now we do the same thing. Let's take a look at the actual expansion here. So we get a term like this. So 1 over r squared can be taken outside, but I get r hat dot r prime, which then here is just a cosine. Okay, which also follows from here. Okay, so let's take a look. I get the, let's see, let's do this correctly. So I get the integral of, again, r over r squared, r minus 2r, this. But now the second part, r squared dr. Now the second part here is now I get an additional cosine theta on top of the sine squared theta that I had before, sine squared theta, d theta, and then I get again just d phi. So from 0 to r, 0 to pi, and then this is 0 to 2 pi. Now this integral, actually, no, let's do it. Let's give you guys 2 minutes to see if you can solve this integral. Okay, let's get back into it. So Harry and Wei Kim are saying 0, but with a question mark. Well, why would there be a question mark? As in, what, why do you think it could be 0? I mean, Harry or Wei Kim, what do you think? Why did you guess 0? Okay, so Harry is using the inverse technique. So it seems like a trap if you ask it like that. I mean, yes, that is very clever because I mean, how many integrals can you solve within the span of 2 minutes? Good, good. That's yeah. Simon, on the other hand, says that theta term should be 0. Simon, can you explain why? Feel free to use your mic.
Just by simple integration, I just look at the theta term, cosine theta, sine square theta, that would be 0.
Okay. If you can do that in the exam, great. I generally prefer if you actually give me an explanation of why that is. Right? Even if you just write it out in words, because it is very important, right? It's yes, some people just see it somehow, but even in an exam, write it out. So let's take a look. Let's see why this could be 0. Okay, Zhao Feng is saying symmetry about pi over 2. Um, right? Although I wouldn't put it this way because that's only half of the story, right? Because yes, there is symmetry, but the question is, what about the symmetry makes this makes this thing go 0? And one simple thing that you can do, for example, here, and this is actually something that we'll need, is one is an even function, one is an odd function. Right? And so when you integrate out this thing here, indeed, you will simply get 0. And so, right, indeed, right. Looking at the symmetries is one way where you can quickly see this. As Aoyang Hoyin is saying, you can also directly integrate it, which is absolutely fine, right? This is absolutely fine. Sometimes, if you're a little bit smart about this, you can also just simply, look at the symmetries of the cosine function and the sine squared function, and from there deduce that this simply integrates to 0. And actually, we will actually see examples. Maybe we won't get to it, but we may see some examples. Okay, good. So this here, indeed, is also 0. So now we have, even a more particular case where, we have an example where there's this sphere which is charged in a particular way, actually gives us 0 monopole, but also 0 dipole. And so the term that we do need to calculate is the quadrupole. So here the quadrupole, for those who are interested, would be integrating r over r squared, and there should be another r squared here. There should be an R here. R squared here, and then R minus 2R, R squared dr, and then there is a integral over 3 over 2 cosine squared minus a half, which is the Legendre polynomial, sine squared d theta integral d phi. Okay, I'll leave you to do this at home to solve this integral altogether. But again, this is simply standard techniques just to solve the integral. And then you get the whole quadrupole. You get the whole quadrupole moment. You get the scalar field associated with the quadrupole moment, and then hopefully we haven't gone too far astray. How would you calculate the electric field? How would you calculate the electric field? Isn't it r cubed in the dipole's first line? R cubed. Why would it be r cubed? Okay, never mind. Good. Okay. Okay, it doesn't matter. If I'll double check the R's, but I hope you guys get the gist. So okay, so once I've found, let's say, phi quadrupole, how do I get the electric field? Take the gradient, negative gradient to be precise, but good, Alex, thank you. So I can simply do this. Okay. So even this different fields, if the monopole, dipole, quadrupole are not all zero, we just add these different fields up. I take the gradient, and boom, I get the electric field of this object. Okay. So yes, typically when you see, oh, what happens if I'm far away from Z or far away from the object, multiple expansion is very useful. Okay, let's do another quick example, and let's do another example. So now instead, let's consider a loop. Let's consider a loop, and let's put this here. I just put it like that. Okay, so let's make this X, Y, and Z. Let's make a loop, and let's give each side some width W, and there is a current I flowing through it. Okay. Again, I'm gonna go very far away from this object, and now I can actually calculate the vector potential, also using the same techniques as we did before. So here, we can calculate the magnetic dipole moment, which again, if I'm considering loops, it's relatively simple. And I've lost this again. Back. Okay. So here it's just I integral over dA. In this case, what is dA? Well, here is just the current again, W squared in the Z direction. And so I can now calculate, let's say, the dipole term to the vector potential. So here I can write Km m cross r over r squared. Okay, or I can do r hat over r, that's fine, it's the same thing. And with this particular m in mind, I can actually write this as follows. Write this as Km, let's see, w squared sine theta r squared in I direction. Okay, so that's the dipole moment. And then I can also, and this is the spherical coordinates, by the way, and I can also take a look at the field here, which is just cross A. And if you go through it, you ought to get something that looks like Km, and I'm just going to keep the M. Oh, okay, that's fine. But just I w squared over r cubed 2 cosine theta r hat plus sine theta hat. Oops. Okay. My technology is failing me today. Okay, so it's relatively simple to use the multiple extension. Right? Which we're typically left with integrals that are reasonably simple to do. These are either integrals simply over, or, either do it in spherical coordinates or fine, and then you get a triple integral that you need to do. Okay, typically keep the first term, and then we're good to go. Okay, any questions about these two examples? Again, the last example I went a little quick, but I just wanted to show you kind of the steps that one would need to go through. Okay, why don't I do the following? Let's take a 5-minute break. So we'll come back at 5:50. And if you do have questions in the meantime, leave them in the chat box, okay? I'll see you guys in a few minutes. Okay, welcome back. Let's keep going. So I don't see any questions in the chat box. So glad that the examples were understandable. Again, in the problem set that we'll release this week, we'll give you some more questions to play with that are specifically focused on the multiple expansion. Okay, so you get to play with it again. We will also be releasing the exercise videos that you can take a look. Actually, are people, appreciating the exercise class videos? Is that a good format for people? What do you think? Okay, good. Yeah, I can imagine as well. You can just, at your own pace, sit there and listen, rewind, slow down, or fast forward if you do know this stuff. So I hope that is a good, a useful thing, useful tool. Okay, so let's that kind of more or less ends this part about the multiple expansion. In the remainder of today, we're going to start a new technique again to solve Poisson equation, and this is going to be the most involved one, but also arguably the most powerful one. So let's take a look, and we're going to call this so-called separation of variables. And the reason why we're going to call this will hopefully be clear very soon. So here, separation of variables. And basically what our aim is to keep independent variables. As separated as possible. As separated as possible. And so what do I mean by that? Okay, keeping independent variables as separated as possible. Well, the assumption that we're going to make, okay, and I can't stress this enough, is we're going to assume a solution form separable form. So what does that mean? Well, imagine I've got some phi, which is a function of x, y, and z. And I'm going to make the explicit assumption that I can write this as product of a function big X as a function of just X, a function of big Y, which is only as a function of small y, and a function of big Z, which is only a function of small z. So what we have is a product of functions. Product of functions that only depend on a single variable. Now, let's see if we can kind of get a grip on how this is how this could be achieved. So let me put three functions here for you. One, that is x, y, z squared. Two, x, y plus z. Three, z, x squared plus y squared. And so the question here, and I'll give you a minute or two to think about it, is which one of these three functions are separable? I'll give you a minute. Okay, 1, 2, or 3. Which ones are separable? Okay, first few answers starting to come in. Harry says 1. Choi says only 1. Shen Chi says 1. Anyone want to go for 10? Okay. Yes, there's a secret option 10, which is also separate. Now, okay. Yes, so in this case, if you talk about fully separable, that is only 1, right? So this is separable. This is actually inseparable. And if you want to be, this is partially separable. Okay. Now, that's why I started off with saying that this is an assumption. So if we can write the solution of this form, then as we'll see, we can actually derive solutions in a rather convenient way. Okay. Now, it should be noted that whether the function is separable or not does not have anything to do with whether there are any connections between the function x, the function y, and the function z. Okay, so don't make any assumptions now. All that we're saying is that x, there's a function x that does not depend on y and z, and there's a function y that does not depend on x and z, and there's a function z that does not depend on x and y. Okay, there's no, at this stage, there is no explicit assumption on whether these are connected. Now, the second caveat, of course, is that it isn't always possible to find a fully separable solution. Okay? So this method only works for a class of problems where you can achieve separable solutions. And I just want to, again, give you a quick minute to think. Okay? Under what circumstances do you expect there to be separable solutions or not? Okay, I'll give you a minute or two to think about it. But I really hope that you can start building some intuition for for these various methods and how to best apply them. So, under what circumstances do you expect these solutions to be separable? So Brian is saying if the equation is separate, which equation are we talking about? You mean the Poisson equation? Zhao Feng is saying linear PDE with linear boundary conditions. I don't know what IBVP means. Boundary value problem. What does the I stand for? I'm going to say inverse. Initial boundary. Okay. Sure. Initial boundary value problem. Okay, that is a very broad class. Linear PDEs, linear boundary conditions, not so much. It's actually it's much simpler, right? It's all about symmetry, right? With all of these things, it really depends on whether there's a high degree of symmetry. If I have some odd function where all these different variables are mixing up, and you could even see, for example, right, like something like this, right? This is still separable, even though it looks very clunky. But if I have something that wouldn't be separable, then I don't expect the system to have a high degree of symmetry. So it is something that what you'll often see is when we look at certain symmetries in the problem, where that is usually the case. And so in this case, what we end up seeing in about a week, maybe a week and a half, we're going to take for this topic, is that it really depends on the coordinate system that we end up choosing. Right? If I have some spherical symmetry, I'm not going to try to solve things as separable functions of x, y, and z. Right? Then I'm just going to use r, phi, and theta. And so in this case, the x, y, and z, the Cartesian coordinate system, is useful for when we talk about things like boxes and stuff, infinite planes. And that's something that we'll end up seeing. Okay, so we've looked at, okay, what does it mean for things to be separable? And we've gotten a little bit of a intuition for it, hopefully now. So let's see what we can actually do with this. And so let's take a look at our first part of the story is the Laplace equation in Cartesian coordinates. And so let's write down the function and the equation. So we've got Laplace equation here, which is simply partial phi partial x squared plus partial phi partial y squared plus partial phi partial z squared. Squared equals to 0. And so now, what we'll see is that we actually can get useful solutions out if assume solution of the form of phi, x, y, and z is given by big X as a function of x, big Y as a function of small y, and big Z as a function of small z. So then the Laplace equation becomes, well, 0 equals to second partial derivative of x, y, and z plus the second partial derivative in x, y, and z plus the second partial derivative with respect to z of, again, x, y, and z. Okay. And so now we know that each of these functions, x, y, and z, only depend on their respective variables. And so when we take the partial derivative with respect to, let's say, x, then I know that y and z simply factor out, and I'm getting that the second derivative of big X with respect to small x. And here I get x and z that factor out, x and z, and I'm getting the second partial derivative y, and here the last one, x and y factor out, and I'm getting the partial. Z is a very difficult to make the distinction between small caps and big caps. Add a little bit of sheriff to it, just so that people can see the difference. Okay. And now I can make this a little bit more easy to read. So this is x prime prime y z plus x y prime prime z plus x y z prime prime. Okay, in this case where prime is the ordinary derivative. Because again, remember, since x now only depends on small x, the coordinate x, the partial derivative turns into an ordinary derivative. Okay. So now we have a little bit more magic to do. Divide out both sides of the equation by x, y, and z. So divide by phi x, y, and z, right? So we divide both sides of the equation by phi, and so what do we get? We get this equals x prime prime over x plus y prime prime over y plus z prime prime over z. Okay, so indeed here, if I divide by x, y, and z, the functions x, y, and z, I get, the y and z cancel, and I get x prime prime over x. And similarly for the other terms. So that ultimately I get something that looks like this. And now what do I have? I have a sum of terms, right, that only depend on a single variable. So every term in this sum only depends on one variable, right? So the x prime prime over x depends only on x. The y prime prime divided by y only depends on y. And then the z prime prime divided by z only depends on z. Okay. And so this makes our lives much easier. Okay. Now, why does this make our life easy? Well, if this is the case, and if it's true for all xy, so if true for all x, y, and z, well, then each term must separately equal to a constant. What does this mean? Well, imagine the following. Imagine that this only depends on x, this depends on y, and this depends on z, right? And that's the initial premise. Now, because each of these terms only depend on one variable, and this equation must be true for all x, y, and z, Okay, so even if I vary x, and this equation must still hold. The conclusion, the only way to make that general is that x prime prime over x equals to a constant. Similarly, y prime prime over y equals to a constant. And z prime prime over z equals to a constant. Because if it's a function of, let's say, z, if it becomes a function of z, then I cannot generally make this true. Because I know that x prime prime over x is only a function of x. So if there's some residual dependency on, let's say, z, and this, for example, has some residual dependency on x, then I can't, generically make this equation 0 equals, like Poisson equation. I can't make this true. And so each of these, x prime prime over x, y prime prime over y, z prime prime over z, must individually, separately, depend on a constant, which therefore leads me to that there is one equation with three constants. Okay, so we have some freedom that we need to work with. Okay, we have some room. So three constants here that that I can in principle make anything. Of course, you can almost always guess it. We have the boundary conditions that we then consider. Okay, now under this, in this form here, what we can do is actually make this equation explicit. So in this case, what do we have? We have that the independent equations are given by x prime prime over x, and let's call this minus L squared, y prime prime over y equals minus m squared, and z prime prime over z equals minus n squared, right? In this case, where L, M, N are constants. And so the crux of this story is that we have turned a PDE, a partial differential equation, into several ordinary differential equations. But, right, and these ODEs are connected by constants that satisfy an equation, right? So we've seen this before. Oh, sorry. We've seen this right here on this slide before, is that, I know, in this case, I know that, minus L squared minus m squared minus n squared should then equal to 0. So I've turned a partial differential equation into three ordinary differential equations plus a fourth equation that connects all of these L, M, and N's. So this is a handy trick where we can actually make things simple or simpler. Now, let me close out by, if I look at the form here, I can actually get the general solution. It's actually not that hard, because what are the solutions to these three equations that you see here? I'll give you a minute. What are the solutions? exponential. Indeed, very good, Jeffrey. So these solutions are simple exponentials. So I can write x as a function of small x being a to the I lx. Of course, we have another one, which is b e to the minus lix. Have in y as a function of small y, we have c equals e to the I m y plus d e to the minus I m y, and we have z as a function of small z, and we can say big E equals e to the I n z plus f e to the minus n I n z. Okay. Now, we could also actually write these solutions in a slightly different form. I can also write big X of x equals a, and I'm going to put a little prime, just not to confuse with the equation here, but instead I'm writing cosine of lx plus b prime sine lx, and the same thing for y, which is a c prime cosine my plus d prime sine my, and z simply be prime cosine nz plus f prime sine nz. Okay. So I have now, generic solutions to big X, big Y, big Z, and I know, the way in which they have to be combined. So I know the relationship between L, N, and N. And so we can actually now, we can have the full solution to this problem. The only challenge, and this is what we'll then discuss next lecture, is how do I get all of these constants, right? These A, B, C, D, and F's. What is A prime, B prime, C prime, D prime, E prime, F prime. And that then, is intimately connected with the boundary conditions. Okay, now this is a good moment to stop the lecture for today. Let me open up the floor to see if there are any questions. Again, first on the record, and then I'll stop the recording and to see if there are other questions as well. So, okay, let's open up the floor. Are there any questions? I haven't seen any questions. Okay. I'm gonna start counting down, going once. Third last slide. Okay, this is 1, 2, this is the third of the last slide. Go for it, Harry. Okay, well, sorry, there's another question. Are the constants real? Okay, just gonna address Harry's question first. Yes, that's a second derivative, thank you. And Len Chunhua is asking whether the constants are real or not. Well, in the end, they have to match with the boundary conditions. So somehow these solutions, look at, for example, here, then, well, imagine that I can write down a solution where these A and these B's and so on are not real. Well, how would I be able to? It would be very, very awkward. But yes, generally these A, B, C, D's are real. But because we're considering a physical system, of course, if we're considering kind of Laplace equation for complex fields, then you could in general get other form solutions. But since we're here only considering phi to be a real field, generally the constants are also real. I wouldn't be able to think of a way in which I could make those complex but get the phi to be a real thing. But maybe they're very clever people who could do that. No problem. Thank you for asking the question. Okay. Any more questions? Going once. Going twice. Okay. Stop the recording.